we shouldn't think of a Big Bang as an explosion going off in some pre-existing larger space, like a fireworks or something like that. Because our version of the Big Bang is that space itself was created then. The Big Bang, in some sense, is all around us.
The matter we're made out of and the place where we are right now was inside that universe. The universe has expanded for 15 billion years or so, and it's cooled off, and galaxies have formed, and stars have formed, and planets and people have formed, but we're still inside. And so the Big Bang happened everywhere. It happened all around us, and whatever direction we look in space, we're looking out into the Big Bang.
The most amazing thing about doing astronomy is this idea that all the history is laid out in front of you, that you can look back in time and see the beginning. It's hard. Things are far away or very faint, but just the knowledge that you can look at history in real time, as if you could look back in Earth history and see Babylonians or people living in caves in France, I mean, is a really amazing thing. And although we can't see all the universe at any one time, we can see different pieces of it at different times, and that gives us the ability, we think, to describe its history, even though we weren't around for most of it.
Working with fragments from the dawn of time, astronomers, like cosmic archaeologists, have been piecing together a story of the birth of the universe and how it came to be as we see it today. One of the oldest mysteries in the study of our universe is called Olber's paradox. It begins with a simple question.
Why is the sky dark at night? First, why is that an interesting question? Let's think about it. The universe is filled with stars and galaxies. And if you look in any direction, that way, up, down, eventually your line of sight is going to run into the surface of a star. So that by this argument, you would expect that the night sky ought to be as bright as the surface of the sun or of a typical star. But you go out at night, and obviously it's not. Why?
Now, one lesson that we've learned in the history of thought is that when you have a paradox, it often is because you're using the wrong paradigm. And the paradox is a signal, it's a doorway, leading you to a change in the way of thinking that may enable you to grapple with nature on these much larger and smaller scales.
Until the early 20th century, the universe appeared to be ageless and filled with an infinite number of stars. However, for the night sky to be dark, at least one of these assumptions had to be wrong.
The night sky is dark because the universe is not infinitely old. Olber's paradox is important because it tells us exactly that the universe is not eternal. The universe had a beginning, and Olber's paradox is the evidence that there had to be a beginning.
When you look out at the universe, you are seeing only a finite amount of light from a finite number of galaxies, because the universe is a finite age. Radiation from the most distant galaxies in the universe hasn't even gotten to us yet. And as we look out into it, we are seeing farther and farther back into time. And we are actually seeing far enough back into time that we are seeing regions of space where there are no galaxies because they hadn't been formed yet.
This realization that the universe was far different than we had previously imagined began with a crucial discovery made in 1929. From Mount Wilson Observatory, astronomers Edwin Hubble and Milton Humason found the first evidence that the universe is expanding.
Einstein's general theory of relativity had predicted the expansion of the universe, although Einstein himself had not. Einstein did not know that that prediction was contained in the theory, and when it was pointed out to him that the theory necessarily mandated a dynamic universe, either expanding or contracting, Einstein, because the astronomers told him there was no evidence of such a thing, altered the equation to make his theoretical universe stand still. Meanwhile, in California, not just a few years later, Hubble and Humason were charting the redshift in the light from galaxies, which was the evidence that the universe indeed was expanding.
This 100-inch reflector was completed about 13 years ago and has contributed in 3 or 4 very notable ways to progress in astronomy.
The expansion of the universe, as measured by the velocity of the distant galaxies away from the Earth, has been put into a mathematical expression called Hubble's law. Hubble's law very simply relates the velocity that the galaxies are receding from us and the distance they are away from us. The farther they are away, the faster they move.
Well, we talk about galaxies receding away from us, but it's not quite the right picture. It's not as if space is a big empty hall or theater in which galaxies are racing through. In fact, the whole theater is getting bigger. The universe is expanding and carrying the galaxies with it. Now, to us, this looks like a velocity, but it's not quite the same thing as seeing galaxies racing through space. They're actually racing along with space, away from us.
The classical analogy, which is used in almost all basic astronomy classes, is that of a balloon in which one can look at the galaxies, in this particular case, are like the dots on the balloon. If we look at the expansion of the universe, the expansion of space, from the perspective of, say, an observer on the Milky Way galaxy, we see that galaxies in all directions are moving away from us as the surface of the balloon inflates. There is no center to this expansion. The universe is a continuous surface, and if we were an observer sitting on any other galaxy, we would see exactly the same thing that we see from our Milky Way. We would see galaxies in all directions expanding away from us.
Suppose that in the next hour the size of the Earth were to double. Put yourself in any city, Chicago, let's say. You look out through a telescope at a city that's 1,000 miles away. It's going to double its distance in 1 hour, so it must be traveling 1,000 miles an hour. If you look nearby at a suburb like Winnetka, say 20 miles away, it's only traveling 20 miles an hour.
Astronomers, in fact, observed more distant galaxies receding at greater speeds from our point of view. This is the Hubble law. The further the galaxy, the faster it moves away, and the greater its redshift.
Redshift is also possibly the most useful tool for estimating how far back you're looking in space. When you get a distance, you also know the light travel time, and so you're looking back in time, that concept of look-back time, because that's the light that's arriving here today. We used to come up here not too long ago and work with instruments that you had to ride around in this cage all night, and on nights like this where it's only about, oh, I don't know, 40 degrees, 30 degrees. It's pretty uncomfortable, but that's what you had to do. Now there's so many robotic devices that you can add that you can make this all remote controlled down from the data room.
Okay, we're ready to roll if you are.
Ready. Okay. So what you're seeing here is a look through time. You're seeing galaxies here at 4 billion light years back, and now you're talking about an appreciable distance back toward the history of the universe and its birth in the Big Bang.
The discovery of the expansion of the universe stunned scientists and sent them scurrying for an explanation of our cosmic origin. Eventually, 2 competing theories battled for scientific acceptance.
Part of the Big Bang theory, what we today call the hot Big Bang theory, was the work of Georges Lemaitre with his primeval atom theory. This was first glimpsed not long after Hubble and Einstein had done their epical work. Because Lemaitre was not a great scientist, only a few people heard of his theory at first, but he kept stumping for it and was a good-humored guy, kept showing up at scientific conferences and talking about it. And it began to draw the attention of big-name scientists.
The Big Bang theory proposes that the universe, that is to say all the matter, all the energy, and space-time itself, formed from an initial tiny volume, smaller than the head of a pin, we formally say a singularity, which exploded outwards for reasons at present unknown.
The Big Bang is the popular name for the theory of the expanding universe. It's actually a complete misnomer because there was no bang and it wasn't very big.
In fact, the name the Big Bang was invented by Fred Hoyle to make fun of that model. on a BBC radio show in 1950, Fred Hoyle coined the term the Big Bang because he was making fun of the model that started with a hot, dense situation and evolved.
People in the 1940s and 50s were aware of problems with the time scales in cosmology. If you took Hubble's inferred expansion age for the universe, that, using Hubble's data, turned out to be less than the age of the Earth. This led to problems.
So there was a flaw in the theory. The expansion, however, seemed to be real, and so some other theorists, a group led by Sir Fred Hoyle, proposed an alternative cosmology called the steady state, in which the universe expands all right, but it never had a beginning. It's infinitely old.
It was a way of explaining the Hubble expansion without having the early universe be hot and dense. The idea is that as the universe expands, new matter is created to fill in the gaps, keeping the density of the universe the same. So even though parts of matter are moving away from each other, you make new matter to fill in the gaps, so the average amount of matter per unit volume, the density, stays the same.
The steady state theory suffered from two problems which led it to its abandonment by most scientists. One was that in a steady state universe, some galaxies should be much, much older than others, and as more and more galaxies were cataloged, these ancient galaxies were not found. And secondly, the time problem in the Big Bang theory went away when cosmic distance measurements improved and the chronology of the universe when appropriately changed in response.
And then finally, with the discovery of the microwave background radiation, which is the leftover primordial fireball from the Big Bang theory, and there was simply no explanation for that in the steady state theory. So the steady state theory died.
The very same observations that killed the steady state theory gave new life to the Big Bang. Slowly, these observations revealed the imprint of an evolving universe.
Astronomy is an observational science as opposed to an experimental science. That means that we observe things with our telescopes, and then theoreticians attempt to explain our observations. It's very difficult to design an experiment which can test the theories which are worked out, the way a classical scientist would do. An almost unique example is the example of the cosmic microwave background radiation, in which the existence of this radiation was first proposed by George Gamow back in the 1940s, who first worked out the theory of the so-called hot Big Bang.
Gamow reached an astonishing realization, and that was that if the universe had been tremendously hot in the past, it couldn't be totally cold today. There must still be some residual heat left over in the universe. That prediction was ignored at the time.
In 1964, two radio astronomers who had just moved to Bell Labs to start using a small telescope that had previously been used for satellite communications began mapping the Milky Way with unprecedented accuracy. And they noticed when they tried to calibrate their receiver, a uniform buzz or noise.
Arno Penzias and Bob Wilson found that there was a little extra noise in the instrument that they could not account for.
We eliminated just about everything, and then the only possibility was that it was coming from someplace outside our galaxy, and that seemed like such a far-out idea.
And they went component by component through their instrument, trying to figure out what part of the instrument didn't work. In fact, they thought at one point that the pigeon droppings on the antenna were the source of the extra noise, and they actually had that cleaned off. I don't think that they did it themselves, but they had it cleaned off, and indeed the extra noise was still there.
Meanwhile, right up the road at Princeton University, Robert Dicke and his colleagues were building a tiny microwave horn to listen for the cosmic background radiation. So they knew that in a Big Bang universe there should be this background hiss. Right down the road in Holmdel, two guys at Bell Labs were in fact observing it but didn't know what it meant. Finally, one of them coming back from a conference, chance conversation with a colleague, was brought to make the connection. And Dicke's paper and that of Penzias and Wilson was published in the same issue of Scientific Journal. And a new era opened up, the era of the astronomy, of the exploration of the cosmic background radiation, the so-called echo of creation.
The cosmic microwave background radiation gives us one of the strongest tools for studying the conditions in the early universe. We believe that this radiation is a relic from a time perhaps a few 100,000 years after the initial Big Bang, when the universe first became transparent to light.
Those photons flying on through space would have been stretched out and redshifted down into the microwave radio wavelength by the subsequent expansion of the universe. And every observer in the universe looking out should see a fog of these photons in the distant background, evidence of the light at the beginning of time. That's what the cosmic background radiation is.
When we look at the sky in the microwaves, we see this perfect black body radiation, but at a temperature not corresponding to that of a furnace, which might have been the beginning of the universe, but of 3 degrees above absolute zero.
The Big Bang Theory makes 3 basic predictions about the cosmic microwave background. First, it says that the spectrum of energy level against frequency of the cosmic background radiation should follow what's called a Planckian or black body curve. This was the curve that Max Planck explained when he invented quantum physics. Second, the theory says that the radiation should come pretty much smoothly from all parts of the sky. And third, it says that radiation, although it's smooth, can't be absolutely smooth. It should show some structure in it, because the universe, after all, isn't just a uniform gas. It's full of galaxies and superclusters of galaxies, and traces of its formation should be contained in the background radiation. Now, the COBE satellite was launched to test these assumptions.
Only 2 months after the launch of the COBE spacecraft, the first major scientific results were announced, and that is that the spectrum of the cosmic microwave background radiation was that of a perfect black body with a temperature of 2.73 degrees above absolute zero. A couple years after launch, the COBE Science Group announced their next major result, which was the first detection of temperature fluctuations across the sky in the cosmic microwave background radiation. In other words, the radiation, which is approximately 2.73 degrees, is just a slight bit higher in some directions and a slight bit lower in other directions.
Those fluctuations are extremely small. They represent about 100,000th of a centigrade degree. The fact that we see galaxies at the current day says that the seeds of those galaxies, which we believe formed by gravitational attraction, must have been present in the early cosmic microwave background radiation at a time when matter and radiation were interacting very intimately.
The COBE fluctuations show us these density peaks and valleys as they were when the universe was young and the fluctuations were still rather small. But as the universe expands, the fluctuations continually grow. The peaks get peakier and the empty regions get emptier as mass is pulled into the peaks. After 10 or 20 billion years have gone by, which is where we are today, this nascent COBE structure, which was barely visible back then, has grown. First, galaxies collapsed under their own gravity, and then later, the galaxies formed together in the peaks. Both of those, the galaxies and the groups and clusters, they're all visible in the COBE maps today.
Like the maps of ancient explorers, COBE charts the boundary between what we can observe and what we must theorize. In a sense, it's a map pointing toward the beginning of time.
It's not as though the Big Bang occurred in some part of our universe and then expanded out to fill the rest of it. The very space-time of our universe was born in the Big Bang.
You can imagine the difficulty of trying to author a theory of what went on before there were laws of nature, for instance, what went on before there was time. Still, there are ideas. One idea is that the entire universe began as a bubble in quantum foam, which is the basic foam-like structure of space-time. Another is that the universe began in a 10 or 24-dimensional structure of pure geometry, which for some reason collapsed into a 4-dimensional expanding structure. So there are plenty of ideas. Whether humankind will ever actually know anything about what went on prior to the beginning of time is as much a philosophical or even a theological question as it is a scientific one.
Strangely enough, if we try to look backwards in time to the very early Big Bang, rather than getting more complicated, at least for a certain range of time, our picture of the universe becomes much, much simpler. We can't go quite back to the very initial singularity or the Big Bang at t=0. Our current understanding of physics is not sufficient.
Cosmology begins at the Planck time, which is 10 to the negative 43 seconds after the beginning. Before then, we have no theory, we can just speculate. From 10 to the negative 43 seconds onwards, Einstein's gravity theory describes the universe.
A popular idea which comes from particle physics is that at this time, all of the basic forces, the fundamental forces, gravity, electromagnetic, the weak force, and the strong nuclear force, were united in what one calls a grand unified theory of the forces. At a time of about 10 to the minus 43 seconds, theorists believe that the gravitational force parted company from the other forces and began to look much as it does now as a gravitational force.
What happens is that the universe is very hot. There are no particles as we know them. There is essentially radiation, pure energy. Radiation does create particles, exotic particles, which come and go until eventually, when the temperature becomes low enough, ordinary protons and electrons can be created out of energy. All of this happened in the first microseconds of the universe.
All the matter was in a very hot plasma. That means it was ionized into electrons and protons. And the universe was basically a smooth, hot gas, expanding quite rapidly and cooling quite rapidly. But there were no lumps and no concentrations of matter in that early universe.
As the universe expanded, it cooled. And as it cooled, the ability of different early species, protons, neutrons, electrons, and so on, to be created out of this reservoir of heat energy gradually diminished. At a time, say, 100 seconds after the Big Bang, the numbers of protons and neutrons were roughly frozen. About 5/6 were protons, about 1/6 were neutrons. Before that epoch, the universe was so hot, collisions between particles were so strong that the atomic nuclei could not hold themselves together. But at a time of about 100 seconds, when the temperature is maybe 1 billion degrees, the lightest elements, the lightest atomic nuclei could form.
Now, what happens in Big Bang nucleosynthesis is what happens in a hydrogen bomb. A hydrogen bomb converts hydrogen to helium. That's the main thing that goes on when the entire universe went through this hydrogen bomb state. It converted hydrogen to helium. In fact, we can calculate that for a standard Big Bang model, you should convert about 1/4 of the mass of the entire universe into helium. That's observed. That's what we see.
Physicists calculate that during that time, the entire universe was like the hot, opaque core of a star. After a few minutes, these intense nuclear reactions ended as the universe kept expanding and cooling. Not until nearly 1 million years later did the universe cool enough to become transparent.
In the first few 100,000 years of the expansion of the universe, the density of matter would have been so heavy that photons, the particles that carry light, couldn't travel very far. In fact, couldn't even travel the diameter of an atom before they would just run into another solid object, a proton, in most cases, and be reabsorbed. A universe like that is opaque, but it's constantly thinning out as the universe expands, and there comes a point when the density of matter drops below the point that it can still trap photons, and that's the era of let there be light. All the photons are released.
At this particular time, the radiation and the atoms, the matter, parted company. This is the time from which we see the so-called cosmic microwave background radiation, which is one of our strongest probes of the conditions in the early universe.
When the universe finally cooled to the point where electrons and protons could join together to make hydrogen atoms, things began to happen. This smoothness that was characteristic of the universe began to break up into lumps that would eventually form galaxies and stars. This was prevented from happening earlier, but once neutral atoms formed, the kind we see that we're made of, then the universe could begin to cool and make lumpy structure.
The matter, which would interact gravitationally, gradually began to clump under gravity and form galaxies, which would form stars and so on. And some theories suggest that things that looked sort of like galaxies might have formed, say, by 1 billion years after the initial Big Bang.
This is perhaps the most important aspect of the Big Bang, that the universe was very different in the past and that it has been evolving steadily since that creation event. So to actually observe that, to show that galaxies are not quite the same as they were 4 billion years ago or 8 billion years ago, but that there's an evolution process, much in the same way that there's an evolution of life on Earth, is a very important thing.
And my own guess is that a century from now, the Big Bang Theory will look rather different and hopefully be much more sophisticated. There'll be a lot more going on, but it'll still be within this general arena of realizing that the universe, as we know it, had a beginning at some finite period in the past, some 10 or 20 billion years ago, and that it has been expanding ever since from an origin in high energy, from a birth in fire.
All around us, the universe holds relics of its birth, fragments hidden in the deepest regions of space, and the tiniest traces of atoms. We are only beginning to understand the astounding evolution of the universe and our own surprising journey through time and space.